So I am a software engineer by training. I never actually worked as a software engineer. I've always been kind of gravitating around the DevOps SRE world for some reason. Yeah, just doing a lot of Linux stuff when I was young, and then I graduated to cloud. I specialize on cloud native stuff, so anything around GKE. And today we're going to talk about service mesh, what it is, what it's used for, and what does it help us solve. I will also link you to an article I wrote about why you shouldn't use a service mesh, because I provide full service to why and why not. So a long time ago, monoliths were cool. To some people in this room, apparently tonight, they are still cool because they're still doing monoliths. But to a lot of people, yes?
They're cool if you use them correctly.
I am not saying they're not cool. They are cool. Before we move on, how many people are actually doing monoliths today? 2 people. How many people are doing microservices? How many people are doing microservices on Kubernetes specifically? How many people doesn't know what Kubernetes is? Good, we're in the right room. Okay. So the problem with monoliths, when you don't use them properly, is that they can lead you to legacy because they are very hard to release. You have to plan a release, and you have to bundle in a bunch of code of 3 months or 6 months of work before you can release an application. So some people at some point, and I'm not going to judge whether they were clever people or not clever people, decided that a way to solve a monolith is to just wrap it around an API. Just put an API on a monolith and it will become good. And that's what I call putting lipstick on a pig. So a few years back, this idea of API gateway started bubbling up. And the idea was that you have API gateway, which is the contract to how you can call an application, right? And if that contract change, you have best practices around how you change that API. Now, at some point, people were like, screw that, let's just rewrite everything. That's the dream of every single developer. That's how you guys keep job security. Rewrite code. And then they started saying, like, oh, why don't we move to this thing called microservices? So microservices are basically small, loosely coupled services that can talk to each other, can scale separately and independently. I don't have to define what microservices are. And a few years back, I think about 7 years back, Docker came up with this thing called containers. So just FYI, spoiler alert, containers existed in Linux for a very long time. Docker just democratized how people can use containers, right? All the stuff that are under containers are just kernel things that existed since ages. And another thing is, before Google, I worked for a company where we were actually a service provider, and we were doing something similar to Cloud Build. We were running untrusted code in our environment, so we had to come up with an idea of how to containerize them. So I spent 10 years of my life actually learning how to use Z groups and namespaces and CH root and stuff like that. And it was like pretty terrible. Actually, Docker is great. So containers are great for microservices, right? They're immutable. They avoid the thing of works on my machine. You go, your DevOps person going to developer say like, hey, there is code errors in this thing. It's like, it worked on my machine. So containers avoid that because basically you can build a container on a machine, run it on a different machine, as long as it's the same operating system. And by same operating system, I mean Linux. Windows, for some reason, decide that they don't want to support containers. Well, they do now, but they did it very recently. But basically, as long as you're within the same kind of architecture, so x86 Linux, it will just work pretty much on any Linux box, Mac box, whatever, right? They can be bin packed. Bin packed basically means you can build containers from containers, right? They are lightweight. They're very easy to start. But they have a problem. Managing containers at scale is an issue. Managing 2 or 3 containers to run your personal blog is easy. You just use Docker Compose, and then it works, right? Managing thousands of containers is not doable manually. So yeah, that's kind of the day 2 problems, as we call them. Day 2 problems is the first day you containerize your application, and then the second day it's broken, then you have to fix it. And then there's a lot of other things that you have to take care of, like scheduling, scaling, properly utilizing your environment, connecting your containers together, service discovery, access control, all of these problems, all of these are things related to containers day 2. So some smart people about 6 years ago came up with this thing called Kubernetes. By the way, there is a documentary on Kubernetes on YouTube. How many people watch that? All right, so if you're not aware, there's this company called Honeypot. They created the 2 parts or 3 parts documentary about Kubernetes, 2 parts. And in it, some people from Google and some people from Red Hat and some people from other companies are actually talking about how the whole idea of Kubernetes came to exist, right? It's great if you have 1 hour to waste. So Kubernetes solves the problem of running containers at scale. That's essentially what Kubernetes does, right? You set up Kubernetes and then you just tell it, hey, run 1,000 replicas of my container, and it will do it for you. Kubernetes has this concept of clusters. A cluster is basically just a combination of machines that work together. There are actually 2 ways you can think about Kubernetes. It's both an abstraction over infrastructure. right? You can take a bunch of nodes, you install Kubernetes on them, and then you just need to talk to the control plane of Kubernetes. You don't really care about how the nodes function, and that's good. Kubernetes will make sure that your containers are spread properly. If one container dies, it will recreate it. If a node dies, it will redistribute all the containers on that node to other nodes that have capacity external. But it's also a controller. So the controller concept of Kubernetes is a pretty powerful concept. So what is a controller? It's essentially a loop in which you tell Kubernetes what you are trying to do, and that's what we call intent. So intent is the YAML file, a deployment is intent, right? You tell Kubernetes, I want to deploy this application, and I want 3 replicas of it. There is a control loop, a deployment controller is called, that will look in the cluster, current state. There is no 3 replicas of this container. It will look at etcd, which is the source of truth. That's where all the information of what needs to happen is stored. We're going to talk about it a little bit later. And then it will act on it. So if you're trying to run 3 containers of an application and there is no 3 containers of the application, well, it will just spin them up, right? That's a controller. But you can actually take the concept of controller and do a lot of things with it. So one of my favorite examples is this thing that we have in Google Cloud called KCC, the Kubernetes Config Connector, which basically allows you to deploy Google Cloud resources from Kubernetes. So if you need a VM, you just have a YAML file that says, I want virtual machine, I want this amount of CPU, this amount of memory, this amount of disk. You submit it to your Kubernetes cluster, which has KCC enabled on it, and it will create the VM for you. That's essentially Terraform without Terraform, kind of, right? So that's the controller loop. And you can also build your own controllers, yes?
But is the VM cost competitive to the other platform solutions?
Our VMs are not cost competitive, no. Google Cloud VMs are very expensive, okay, if that's your question. But the VM was just an example. Basically, you can create any sort of resource from Kubernetes, right? That using the controller pattern in a way.
Could you create a Google Cloud build system?
Yes. I don't know. There is if you go look for KCC supported APIs, there is a page that lists all the stuff that you can create from KCC. I think most of the stuff that KCC supports are things that's usually an application need. So if you're deploying an application that needs a database on the PubSub topic, you could actually package all of that in the form of YAML files. So you deploy your application on GKE, but then you deploy all its dependencies the GKE way. Does it make sense?
Yes.
So very briefly, Kubernetes architecture. You are here, you are the user, the SRE, the DevOps, right? You interact with Kubernetes using API or using the CLI. Most people use CLI. A lot of people like to use it kubectl. That's the wrong way to say it. It's kubectl. Or you can use the UI with the Kubernetes dashboard or any other dashboard. Then you're talking to this red box. That's the control plane. The control plane is, or what people typically call it, the master node. You can have 1 or multiple master nodes, right? Typically, in a production environment, you will have 3. If you use GKE, which is our managed Kubernetes, you can create what we call a regional cluster, and the regional cluster will have 3 nodes at no extra cost, so you get the benefit of HA without paying for it. Inside of it, there are a lot of components. The 4 main components for a control layer under Kubernetes are etcd, is distributed key value store, right? That's where the state is stored. The API server is a stateless workload that basically is the point of entry to the cluster. You interact with it, and all the other components interact with the API server. Everybody talks to the API server to read what's in, or write to etcd. The controllers is what we talked about, is the thing that does the control loop. You have the scheduler. The scheduler is scheduling things. So when you tell Kubernetes deploy a container, what happens typically is that the scheduler, so Kubernetes has this concept of watch. So a watch is essentially a mechanism by which the API server can distribute updates to whoever is interested in those updates. So the scheduler has a watch on the API server, right? And whenever you deploy something, so whenever you send something to the API server and the API server stores it in etcd, it tells the scheduler, hey, there is something, right? There is new container that needs to be deployed. Then the scheduler will find a node. You can have 1 or multiple nodes, obviously, on which there is capacity and that meets the demand for that specific application. And it will just tell the API server that container needs to be stored, run on that node, right? Mm-hmm. After that, the API server will call something called the kubelet. The kubelet is a component on every single worker node that talks to the API server to either get commands, so what should I do, or to tell it the state of the node, right? So the API server called the kubelet and say, hey, start this container. The kubelet will call the container runtime, Docker, containerd, whatever, and then start the container. So essentially, the kubelet does Docker run on your behalf in a way, right? Instructed by the API server. There are a bunch of other stuff here. There is something called the kube proxy, which is technically not a proxy. Basically, it's not sitting between the user who is calling an application and the container running that application. What the kubeproxy does is it just manages IP table rules on the node to make sure that pods can talk to each other, containers can talk to each other. And then you have a bunch of other stuff. You might have like some DNS servers, you might have a metric server, you might have some login, monitoring, stuff like that on the node. But that's in a nutshell how Kubernetes works.
Recently, I've been into this licensing issue, the Docker thing, the license thing. So how do you give if suppose if I want to build an image and I don't want to use Docker Enterprise, what should be the?
I use Cloud Build, and I use Podman to run it.
Okay.
Yes.
But also the open source solutions that substitute Docker for something else anyway.
So GKE we dropped. Well, so okay, we're taking the conversation somewhere. So initially, when Kubernetes came out 6 years ago, it only supported Docker because Docker was the only container runtime that existed at the time. The problem with Docker, or the two problems with Docker, is that A, it's a monolith. B, it's a beast. It does a lot of things. You can build, you can host, you can do a lot of things with Docker. But in a Kubernetes environment, you don't need all this other stuff. You only need the runtime. You only need the part of Docker that runs containers. And the reason why I said the problem number one is that it's a monolith. It's a monolith, so you cannot decouple the runtime from Docker. So at some point, some people called CoreOS, which was acquired by Red Hat later, came to Kubernetes and said, like, hey, we have this container runtime called CRA-O, C-R-A-O. We want with Kubernetes to support it. And then the Kubernetes community goes like, no, we're not going to do that. Because if they would to support an EO container, it means that they have to build the logic inside the kubelet, right? The kubelet will be responsible for checking which container runtime is available and using it. So all the code will go to the kubelet, which means that the next time a new container runtime comes in, they will have to check in the code into the kubelet. So the Kubernetes community decided to do something. They said, we're not going to support this. What we're going to do is we're going to create something called the CRI, the Container Runtime Interface. The Container Runtime Interface is the way the kubelet would interact with a container runtime. You container runtime people go build integration for the interface, so we don't have to do it. And so in order to keep supporting Docker, which was not, Docker is not CLI compliant, by the way, and did not want to, they created something called a shim. A shim is a bridge between the CLI part of the kubelet and the Docker runtime, right? What happened in 1.23 or 1.24, I don't remember, is that they dropped the shim support. So going 1.23 or 1.24 plus, there will be no support for Docker. So you have two solutions. You either install Docker, install Kubernetes, download the shim, which is going to be supported. It's going to be maintained by this company called Mirantis, which bought Docker. So they will continue maintaining it. But basically, the kubelet dropped all the support for Docker, essentially, right?
Do they have some kind of beef now?
Not really. Okay. So, or you do what we do, and you replace the container runtime by Containerd. Containerd is CLI compliant. It's OCI compliant. OCI is Open Container Initiative, which is basically like a set of specs that define the image format. So Containerd is CLI compliant, OCI compliant, and it's lightweight. It doesn't have things to build the container, which you don't need in Kubernetes, right? You never, ever, almost never build on the node. You build in the build system, and then you just deploy to the Kubernetes environment. Make sense? Mm-hmm. Any other questions? Please. Okay. But believe it or not, Kubernetes doesn't solve all your problems. It actually just gives you more problems. So let's take an example, services and communication. And by service here, don't read the capital S. I don't mean a Kubernetes service. Let's say a service, a microservice, an application. You have a service A, it needs to talk to service B. If it's just basic HTTP, gRPC, TCP communication, it's great. Now somebody comes and say, we want you to add MTLS, mutual TLS, right? So what do you have to do? You have to create a self-hosted or self-signed CA. You have to create intermediary certificates. You have to add the server certificates to service B. You have to add the client certificates to service A, right? Mm-hmm. And then you have to use the certificate to make that communication work. And if service B would to call service A back, then you have to do all of this the other way around, right? Certificates management is obviously hard. No one wants to do that. And as generally speaking, developers don't like to do service management, certificates management. There are a bunch of other things that you might want to do in Kubernetes that are not actually easy to do manually. For example, routing. How do you make services find each other? How do you route traffic from service A to service B, especially if those services run on different nodes? How do you enforce some policies to say service A can call service B, but can only call this API endpoint and can only make get requests? It cannot do post requests, right? If you want to do these things in code, you're going to spend more time doing this in code than actually building your application. And think about all the stuff that you might want to do. So traffic shaping. So like content-based routing, for example. iOS content goes there. iPhone, Android content goes there. Canaries, A/B testing. All of these things, if you want to do them by yourself, it's very hard. So at some point, again, a few years back, people started using this thing that I call proxy libraries. Essentially, you import a library that does MTLS for you, so you don't have to do it yourself. You import a library that can expose a bunch of telemetry, and then you have a scraper to scrape this telemetry, and that's what we call Prometheus, right? So people started doing this thing in code, which is a valid way and a valid reason, but it has two main problems. A, it makes your code not portable because your proxy library is dependent on your environment, right? And B, it's just more code to maintain. And we know that developers don't like to maintain code. They want to write new code, but they don't want to maintain it. So the idea of Istio, or the idea of a service mesh in general, which actually was introduced by Istio, then later Conduit was introduced, and later LinkedIn was introduced, etc., was why don't we delegate all of this nonsense to a proxy which will run alongside my application and will be controllable from a central position. Essentially, my container will have the logic, the business logic for my application. Next to it, there will be a small container that does all the stuff I don't want to do in the code. And in order to manage that small container, I connect it to a control plane. And so I, as an operator, I can talk to the control plane. The control plane will distribute my configuration to all the proxies, and the proxies will enforce those configuration locally, right? So moving essentially all the logic for MTLS, for traffic management, for policies into a container that does only that. So you don't have to do it in code, and you still can do it, but you don't do it in code. So what is then Istio? Istio is essentially a control plane, which is an application, right? And then a bunch of proxies, which are based on something called Envoy. Envoy is an open source proxy that was introduced by Lyft. They had this thing called Envoy proxy, which is written in C++, and they were using it for years. And then eventually, when Istio came into picture as a service mesh, they just looked around and they found proxy. They found Envoy proxy, which was one of the most lightweight proxies, and they just used that. So what is the idea of Istio? Istio has a control plane, right? The data plane is the proxies. Those Envoy proxies are deployed as what we call a sidecar. So a sidecar is actually a reference to, you remember those like World War I motorbikes with like a little attachment where you can sit one person? That's called a side motorbike. A sidecar essentially is a container that runs along way your main container. The sidecar runs with it, and it does a lot of things that you don't want to do in your container application. Yeah?
So strange use case, can you actually have a proxy running outside of Kubernetes? Because we have this problem right now. We have something that's containerized. It's the new service that we're trying to build, but it's trying to talk to monolith, which is outside, basically on localhost. And of course, we run into a certificate problem.
So your monolith runs on a VM.
The new service runs inside Docker. So when it tries to talk to localhost, you run into the certificate problem. It's a container, it's in Docker, but it's enough to get a certificate problem because it needs to communicate outside the Docker environment, basically, to the monolith, legacy monolith that's running on localhost. And they both try to communicate over HTTPS.
What you can do is with Istio, if you have a service mesh on Kubernetes, you can use something called Istio mesh expansion, which basically you take a VM, which runs outside of Kubernetes, you deploy Envoy to it, and then you add it to the mesh. And then whatever runs on that VM becomes just another service in the mesh.
That might be a good solution, actually.
So that's actually typically something that people do for databases. So you spin up a database server, and then you just run Envoy, and then add your database server to the mesh. And then now it becomes a service in the mesh. So that the other services don't really need to care where that database is. They just know that it's an endpoint that I can talk to. So you have like your services, they're running in a Kubernetes cluster. Typically, we see Istio implemented in Kubernetes, except this strange use case I talked about where you can add a VM. But typically, Kubernetes, Istio is designed to run Kubernetes. So you deploy Kubernetes cluster, then you deploy the Istio side control plane, right, which is the thing that will control the mesh. And then you deploy your services, and each service will have a container, which is a proxy running with it. the proxy container, what it does basically is that it intercepts all the communication going in and out to your container application, and then it can implement whatever policies you want on that traffic, right? The policies are pushed by you to the Istio control plane, and they are turned into something that Envoy can understand.
Because that was actually one of my questions when you talked about the proxy. I was thinking, what now it sounds like it is sort of a router.
It is technically a router. It's an actual proxy. It sits in the middle between your application and whatever is talking to it.
Something like a reverse proxy of sorts.
It's sort of a reverse proxy. You can think about it as that.
Does it have any other kind of explicit connections to other part of Kubernetes instead, except
To the control plane.
Yeah, but that's just. I mean, like it can't affect anything else on the local node except being in between traffic.
Technically, no. So if you have a service which doesn't have the proxy, then the proxy will not talk to the service. It will not. It's not in the path.
But that's very useful. Because now I can collapse the where it is in my head. So.
Okay. Does that help?
Yes.
Good. So now, when you have a setup like this, then now we have what we call a mesh, right? Why do we call it mesh? Very important question. I will explain to you. Let's take a hypothetical example. Imagine this is a Kubernetes application. We have two microservices, a shopping cart and a payment microservice, right? A shopping cart have 5 containers. Well, this should be considered that this is called shopping cart. A payment has 3 containers. Typically, in Kubernetes fashion, if you want to make the shopping cart talk to the payments, what you do is you deploy the payment service first, right? Then you deploy a service, a Kubernetes service with a capital S of type cluster IP, right? That service is kind of a load balancer in front of all your payment services, right? So it does 2 things. A, it helps with service discovery so that your shopping cart can find payments. And then B, it does load balancing, right? The internal mechanism for load balancing in Kubernetes is round robin. So your shopping cart, when it's deployed, in order to call the payment service, it will just resolve an endpoint. So it will just use an FQDN, essentially an internal FQDN. So that FQDN is the name of the service, dot the name of the namespace, dot SVC. It doesn't matter. It's an endpoint. It's an FQDN thing, right? So your shopping cart will call an endpoint. That endpoint gets resolved to a virtual IP, which is just a random IP that got assigned to the load balancer that you created. And then that virtual IP will load balance traffic between the payment services. Does this make sense?
This is why people have such a hard time understanding Kubernetes. But yes, it makes sense.
Makes sense, right?
Yes.
This is a typical service A calling service B through load balancer. You don't have to think. You don't have to understand how it works in Kubernetes. You just think about it as you have a load balancer. It's not technically a load balancer, but it's a load balancer, right? So there is a chokehold. There is an endpoint. There is a central thing that all the calls from the shopping carts have to go through in order to make it to the payment. Yes.
What happens? What happens if you use node IP?
Node port, you mean?
Node port, yeah.
It doesn't matter. It could be node port, it could be cluster IP, it could be anything. Node port will have a cluster IP. Every single service in Kubernetes creates a cluster IP. Node port, load balancer, all of them create a cluster IP.
Okay.
So now with the service mesh, we have this magical thing called sidecar proxy, right? And I forgot also to add one here and one here. Let's just imagine that all of them have sidecar proxy, okay? So that little sidecar proxy, one of the things it does is routing, okay? So your shopping cart will still use the same service discovery mechanism to find the payments, right? It will still resolve an FQDN to an IP, right? It's just that your shopping cart, so your application, will resolve payment.google.com, okay? It will send traffic to payment.google.com, but that traffic goes through the sidecar, and the sidecar knows all the other sidecars in the mesh, right? Because part of what the Istio control plane does, what this thing does, is that every single time a new service pop up, it knows about it. The service, the proxy, the sidecar, register the service to this Istio control plane, and then the Istio control plane issue an update to all the other sidecars saying, hey, new service. This is the IP of this service, right? So this means in this example, every single sidecar has a full map of all the other sidecars. And typically it's just IP ports. So when your application resolves payment.google.com, it will get an IP and it will send traffic to the IP. that traffic does not go to that IP. That IP is only used for service discovery. The traffic goes to the sidecar. Then the sidecar will send traffic to the other sidecar after it applies all the stuff that the control plane tells it to apply to that traffic. So if, for example, there is MTLS, an example, with MTLS, your server, in this case, this is the client, this is the server, right? In mutual TLS, the server presents a certificate to the client, but the client also sends a certificate to the server, right? That's why it's called mutual TLS, because both client and server can verify each other certificates. Well, that job is not done by the developer in the code, it's done by the sidecar. The sidecar have the certificates, have its own certificates, and have the certificates of all the other sidecars. So then the sidecar intercept traffic coming from the application. Then the sidecar will go, okay, I'm trying to talk to the payment. Payment has two sidecars, two IP addresses, ports, right? And then it will go, oh, and by the way, the control plane told me that MTLS is enabled. So I need to do MTLS. So it will actually do MTLS on your behalf without you having to do it in the code, right? Now, what does that give us? It gives us a lot of interesting things. One of them is what I call fine-tuned routing. Let's say, for example, you bring up a new version of the payment service. You developed version 2, right? You deploy it somewhere. It has a sidecar. It will have a sidecar. Everything has a sidecar. In the Istio world, there is something called automatic sidecar injection. So you can just label a namespace, and then the sidecar will be automatically injected with your containers. You don't have to add the manifest to your deployment. So the definition of the container, you don't have to add it to your application deployment YAML file. So let's say you bring up version 2 of the payment. You put version 2 somewhere here, and there is a trick in the Kubernetes load balancer thing. You tell it, okay, well, now you send 90% of traffic to these 3 instances, and then 10% of traffic to the fourth instance. It's not going to be 90-10 exactly, because this load balancing mechanism in Kubernetes is based on IP tables, and IP tables are not very accurate. Let's go back to the example I was trying to say. I'm trying to do effectively the 90-10% I was trying to describe is a canary deployment, right? It's a typical thing. You bring up a new version, you want to send a portion of traffic to the new version, see how it reacts, and then you just slowly shift traffic.
Are we going to do that changes in the load balancing config?
No. So here's the thing. You will spin up a new instance of the payment version 2, right? You would configure the mesh. Istio basically has a lot of objects they look like Kubernetes objects, but they are Istio objects. So you have something called a virtual server, a destination rule, a gateway. Like you deploy them like Kubernetes manifests, but they are specific to Istio, right? CRDs? But yeah, it has a bunch of CRDs, and the CRDs gives you the possibility to basically do all this traffic shifting and controlling and all these authorization policies using YAML objects. But I don't want to go too much into the detail. But basically, you would configure, you as a user, you will configure the Istio control plane somehow to say, I want 90% of traffic going from the shopping cart to hit payment version 1, and only 10% to hit payment version 2. But here, what we have is we have a direct service-to-service communication using the sidecars, which means we can accurately do 90-10, right? Why we can accurately do 90-10? Because this sidecar can have a counter that says 1, 2, 3, 4, 5, 6, 7, 8, 9, 2 payment version 1, 10 traffic, payment version 2, 1, 2, 3, 4, etc., etc. Does this make sense? Now, can somebody tell me why do we call this a service mesh?
A lot of service.
All the services have information about others.
Exactly, it's a mesh. All the services talk to all the other services. They don't use the Kubernetes way of routing traffic, they use the Istio way of routing. Make sense?
But
any questions?
Scalable if you have a lot of services and everybody can talk to each other.
That's actually a very good question. And it's a very common problem in Istio. So here is one of the problems that Istio have. And by the way, I have wrote an article about why should we use a service mesh, and I will give you a link to that to read it later. But one of the problems Istio have is that this sidecar thingy is a container, right? So it needs CPU and it needs memory. It actually needs tons of memory and less CPU, because since it's written in C++, it's pretty fast. It can process traffic very fast. But it needs a lot of memory as your mesh is growing. So there is actually a point in your mesh that when you get to, the sidecars will start consuming as many resources as the actual application. Right? Because, why? Because one of the things that the sidecar have to do is it has to keep in memory a routing table to all the other sidecars. And since there is one sidecar per container, as you can imagine, if I have 1,000 containers, I will have 1,000 sidecars, right?
Internal IBFS, perhaps.
So there are actually a couple of ways that smart people are trying to solve this. One of them is using eBPF instead of IP tables, because that's the problem with IP tables. IP tables, you need to keep basically the routing table in memory, right? With eBPF, you can pre-program and cache and do a lot of things. Another proposal I saw, which haven't been implemented yet, is called smart routing or smart caching, which essentially what it does is analyzes the traffic and it only keeps the routing table of the services that talk to each other the most. And then if the shopping cart is configured somehow to call another service that it haven't talked to before, it will go to the control plane and say, like, I don't know where is the service, and then the control plane just gives it the routing table for that service. Make sense?
Yeah. There are a lot of routing the routing protocols in networking.
Well, it's not technically a routing. It's when I say routing, it's actually a very fancy term. It's not really doing actual routing. If we talk about the networking part, all these routing algorithms you're talking about are only responsible for getting updates of where are the destinations and then routing the traffic. Yes. But if you read all of them, OSPF, BGP, all of those, they just keep stuff in memory. Yeah. Like there is a router from Juniper, a company that makes the routing equipment or stuff. There is a specific model that Juniper sells called the MX960. It's a 10-line card, 10 ports, or 100 ports, 100 times 10 gigabytes port router. It's big, bulky, and expensive, and it powers 70% of the internet. Every single ISP in the world have one of those, right? That thing, if you want to populate it fully, so basically populate all the ports, right, and configure it to do BGP, you need to buy, it has like a computing unit, like there are two of them for redundancy, so it has like a computer built in, which runs Linux. You have to upgrade the computing unit. And Juniper tells you, okay, if you're using half capacity, this is the computer you need. If you're using full capacity, there is a point that you get to, if you want to fully populate the thing with 10 gigabytes ports, the compute unit costs $100,000 each. Because you need to get the one that has the more memory on it, because, you know, suddenly it has to keep in memory all the, basically, routing table, right? But routers are really not that smart, by the way, just that they're very dumb. Now, back to Istio. What we talked about so far is a mesh, right? So we have, to keep in mind, we have our application. It's the container that you write. You have a sidecar. It's the container that gets deployed for you by the Istio control plane. You, as a user, you tell the Istio control plane how do you configure the proxies to do whatever you want, right? So you can enforce MTLS. The proxies will be responsible for fetching the certificates, rotating them, and using them to do MTLS, right? You can do policy enforcement. What do we mean policy enforcement? We can say, okay, service A can call service B, but it can only call a specific endpoint and only make GET requests. You can tell that to the Istio control plane. It will tell that to the proxies, and the proxies will enforce it because this traffic here is not encrypted. So the sidecar is able to see everything that the service is trying to do. So if the service is trying to talk to the other service and trying to issue a post or call, it will just say, no, you're not allowed to do that.
But in practice, is anybody doing it? It seems like a road to enormous confusion. But do people want to do it?
Hence my article why you shouldn't do this. You can do routing. So the example like this I explained earlier, the 9010, 9020, you can do actually routing based on headers. You can configure a policy that says if the header has Mozilla, do this. If the header has Chrome, do that. If the header has iPhone, do this. If the header has Android, do that. You can do, of course, service discovery, and then you can do telemetry. This is actually one of the most powerful things in Istio is telemetry. These proxies are actually exposing a bunch of telemetry. So you can just drop a Prometheus server and then tell Prometheus scrap all the traffic, and it will tell you how much bandwidth this thing is using, how much, what does it talk to, how many 200 calls are getting through, how many 500 calls are getting through, all of that without having to do anything in the code of the application itself. So it's pretty neat. Now, let's say we want to get traffic into the mesh or traffic outside of the mesh, right? Well, we have this thing called ingress gateways and egress gateways. So ingress and egress gateways are just a set of special envoy proxies, in a way you can call them, that basically are responsible for either getting traffic from outside the mesh to the mesh. Typically, this is where you will expose your public endpoints. So if you have a front end, an API, and you need to make it available to the internet, you would deploy this behind a load balancer, and that would be your ingress. And then you can do also a lot of policy enforcement here. And then if you want to enforce policies on the way out, so say, for example, that my mesh can only talk to star.googleapis.com, so only talk to Google APIs and nothing else, we can enforce that at the egress level. Yes?
Does it mean the application load balancer, which is like the one in the L service, that is just doing the domain to like a public endpoint facing sort of?
If you would have, yeah, you can have pretty much any load balancer here you want. You can use any type of load balancer to expose your mesh to the public.
Yeah.
Okay. You can also do at the ingress gateway. You can do GW token, GWT, and TLS. So you can actually make the ingress gateway verify a job token of a user before it gets into the mesh, so you don't have to implement it in code.
That's like API proxy.
It's pretty much like an API gateway, except it's not an API gateway. It looks like an API gateway. It's called ingress gateway for a reason, because it doesn't do the things that API gateway does. For example, it cannot do rate limiting. It cannot do error handling or whatever. Like whatever the stuff the API gateway does, this thing cannot do it, right? It just does stuff that is specific to the mesh. Yeah. This is the example I was trying to show earlier. This is how you would do traffic splitting, right, between two services. So I have a new service B coming up, and I want to say 95% of the traffic goes to service B version 1, and then 5% go to service B version 2. You deploy what we call a virtual service. As you can look at it, it looks like a Kubernetes object, right? And then you say, okay, well, my virtual service, which is service B, has two subsets. There is version 1 and there is version 2, and then you can see here there is a weight that says 95%. So this is traffic splitting. You can do fault injection. You can actually inject faults. So you can do like a virtual service again. There is the subset. So here we have 95%, so that's canary. But you can also inject delay of 5 seconds every 0.1% of traffic. Yes?
I feel that fault is way too specific. It can be more generic about what should happen.
No, it's fault injection. It's literally injecting faults.
Yeah, I know, but what kind of faults?
No, yeah, here, HTTP status 400.
Thank you. So
Yeah.
I didn't read that.
Yes.
It's like chaos.
It's kind of chaos engineering, yeah. You can use it to do chaos engineering.
That's good.
You can do timeouts. You can also do retries. So if you are trying to make outside calls to an API and you know that the API has rate limiting, so every random number of minutes you just get like you get a 400 back or a 500 back, you can actually tell the egress gateway to do retries. So you can route all traffic through the egress gateway and then tell the egress gateway, retry 3 times with a 10 seconds pause, and then the fourth time with a 20 seconds pause, and then the 5th time with a 50-second pause. And if none of these calls go through, just do a circuit breaking and just throw a log or like throw a metric somewhere, and then you can catch it and act on it. And you can do all of this using YAML objects because everybody loves YAML, right? So you don't have to do these things in code. That's the whole point, right? Yes.
But can we run Grafana container and get the metrics there from Prometheus?
If you have Prometheus, yes.
Okay.
You can deploy Prometheus to scrape the metrics from the proxies, and then you can deploy Grafana to visualize those Prometheus. But you need Prometheus. You cannot use Grafana without Prometheus, right? It actually runs very well in Kubernetes. It was designed to run on Kubernetes. The control plane is just a pod. It's called Istio. It runs in Istio system, the namespace, and that's how when you deploy Istio by default, it creates an Istio-system namespace, and inside of it, it will deploy multiple things. The main one is Istio. There is also a CA service, so certificate authority service for all the MTLS certificates. There is also the automatic sidecar injection is a pod as well that runs in Istio system, and that's basically the thing that you take a namespace in Kubernetes, you put a special label on it, and then the automatic sidecar injection, whenever you deploy something in that namespace, will automatically inject the sidecar, so you don't have to inject it manually. Well, it's technically not injected. If you want to do manual sidecar injection, you will have to take your deployment manifest for your application and add another block, which is the container, right? If you don't want to do that, which a lot of people don't, they just use automatic sidecar injection. Yes?
You said that the control plane is pod, right?
Yes.
Does it get prioritized? Like if it goes down, then everything is down.
No. If it goes down, the service continues to work because the proxies are enforcing all policies locally.
Ah.
So if the control plane is down temporarily, the mesh will continue to work. What will not what will happen if the control plane is down for a very long period of time is things like this service goes down, right? Then the proxy doesn't exist anymore, but this thing is not down, is down, so it cannot update this thing to tell it, hey, this IP doesn't exist, right? It cannot update the mesh. So if events happen in the mesh and the control plane is down, no one will get updated. But this is stateless. It doesn't have a database. So you can just run 6 replicas of it.
But one question, does it get, because if I'm running 100 pods, does it get more priority by Kubernetes?
No. Okay, so it's a stateless workload that you can just run more of to have HA. Okay. That's it.
Is the control traffic encrypted, or is it like plain text?
It's encrypted. It's HTTPS. Yeah,
okay.
It's HTTPS. It's, if you want to more deep. So these API calls that are basically the calls between the proxies and the control plane are gRPC calls, and they are a set of APIs called XDS. We usually refer them to XDS. X stands for whatever, because there are actually lots of APIs. There is the SDS, there is the TDS, there is multiple APIs. But basically, this thing talks to this thing over an API that this thing understands, right? And one of the things also that is nice with the Envoy is that Envoy can hot reload this configuration without restarting it. So when new things are in the mesh, and the control plane has to update everybody to tell them new things happen, hey, update your routing table, it just makes an API call to the proxies, and then the proxy will just take this information, store it in memory, and then hot reload this configuration. Make sense? So it's actually very instantaneous. Like if you configure things, they happen right away. So gRPC here, this can be HTTP, this can be HTTPS if you enable MTLS, and that's pretty much it, I think. Yeah, so you can do automatic sidecar injection. We talked about that. You can do the Istio control plane, back to your question, gets deployed with a horizontal pod autoscaler. So it will scale automatically based on the CPU usage of that thing. So in a nutshell, what a service mesh does is that it allows you to connect, basically make things talk to each other, secure, MTLS, control, so all the policies, and observe is the observability of the telemetry parts. It allows you to do all of these things in an infrastructure, in the infrastructure layer, technically, because this is a container. So all of this is enforced at the infrastructure layer outside of your application logic in a Kubernetes way. That's the TLDR of what a service mesh does. There are actually a couple of service meshes in the wild. The most known ones are Istio and Linkerd. So Istio is Google plus a bunch of other companies. Linkerd is joint. I don't remember the name of the company. So Istio works with Envoy. Linkerd works with Finnegal and Yeti. Finnegal is an open source proxy. Yeti is their own proxy written in REST. So it's very lightweight. Istio is Linkerd on steroids. Istio comes out of the box with a lot of things. Linkerd comes out of the box with just MTLS, and then you can just add plugins to it to add more features. Istio can do circuit breaking at the network level. Linkerd can do circuit breaking at the request or the session level. They both do routing using versions. They both can do traffic shifting and traffic splitting, so canary, A/B testing, etc. Istio uses the service discovery mechanism of Kubernetes to do service discovery, so the QDNS engine or the built-in DNS mechanism in Kubernetes. Linkerd has another service called Namer, so it deploys things called Namer for service discovery. The load balancing is done on one of them by Envoy, the other one is by the Finnegal or whatever proxy it supports. There is one cool thing actually you can do with the service mesh, and this is where it's very exciting, is that you can create a logical mesh that spans across multiple Kubernetes clusters, as long as they can talk to each other on the network level. This is actually a very powerful thing that a lot of people do, and I did a lot of this shit with banks, is that you can deploy Kubernetes clusters as long as they are part of the same VPC, right? For those who use cloud, as long as they are on the same network and they can just talk to each other. Actually, even if they're not really technically on the same VPC, but usually we don't do that. So we just try to kind of curve the customer interest to this. Just deploy everything on the same VPC. They can be in the US, in Japan, in Asia, and then you can deploy a service mesh that spans across all of them. Istio has something called locality load balancer. So if you have, let's say you have 3 clusters and each of them run the same exact set of services. It's the same apps or the same microservices running in all of the clusters. What you can do is you can configure each cluster to prefer the local service before it goes to the other region. So you can tell it if the service you're trying to call is available locally, route traffic there. If you are taking that service down for maintenance or deploying a new version or something is wrong with that service, then it will route to the next region. Yes.
When I was younger than now, I heard a rumor that if you were going to connect services in Google Cloud between different zones, or not zones,
regions.
Thank you.
Yeah.
Regions, exactly. You need to do complicated VPC connections and stuff like that. Is it possible?
If they are on different VPCs, yes. But if they are on the same VPC, no.
So
Because a VPC in Google Cloud is just one flat network that spans across all the regions.
Thank you.
So pretty much anything that is in one region can talk to anything else that is in another region. There is one caveat with that, is that there is inter-region traffic, so you will pay for it.
Yeah, of course, we pay for it. I mean, yeah.
No, but like egress costs across regions, right? If there is like, because in GCP you pay for egress and you don't pay for ingress, right? So if services across two regions are talking to each other and they're very chatty, you might end up with a very hefty egress bill. But that's why we have salespeople that just talk to the customers and give them discounts, so they don't end up with that.
Okay.
Those are the questions, yeah.
Does it work with private clusters as well?
Yes, so that's the thing. Private clusters, you mean without public IPs?
Also like along the way, underlying.
Yes, I didn't want to go into that because it's too complex, but yes, you can. If you have a cluster running on-prem, and then you have some sort of VPN or interconnect, whatever, you have something that connects the cloud to that cluster, you can either spin up, deploy the Istio service mesh on that one, right? And then you would use the ingress and egress gateway to connect them. So this cluster will use its egress gateway, and the other cluster which runs on-prem, which you can see in the screen, but just imagine it's there, that one will have an ingress gateway. So your services running on cloud will call the ingress gateway to get routed to the service that runs on-prem. Make sense?
Yep.
Any other questions? You want to get started? There is a lot of ways you can get started. I would recommend you to, well, obviously use GKE because it's awesome. But there is something actually called Anthos Service Mesh. So Anthos Service Mesh is a managed version of Istio that we have right now in GCP. And basically, it means that we run this for you. So you don't have to take care of that. We run it on our own infrastructure. So it's just available there for you. And very soon, we will be able to also run this for you. So we will be able to manage also the proxies. So you don't have to care about that. So you can just create a Kubernetes cluster, GKE, and say, like, give me Anthos Service Mesh, manage everything, and then magically it works. You just need to inject, so to label your namespaces to get automatic sidecar injection, and it just works.
But I thought Anthos was running things on AWS or private hardware.
Anthos is a lot of things. So Anthos is actually an umbrella product that has a lot of things under it. But yes, in Anthos, one of the offerings we have is the ability to run GKE on other clouds. So you can run GKE on AWS, you can run GKE on Azure, you can run GKE on-prem with either VMware or directly on bare metal. But that's just the base. So Anthos Service Mesh is something that adds up on top of all of this, which is managed mesh.
Because you prestige
GKE, yes.
Or as a kind of an add-on.
What's the Anthos Service Mesh or the?
Yes, what we can always include is this kind of, is a merger with Google Kubernetes Engine.
So yeah, so Anthos as a product in general, you can consume it two ways. You have a subscription model where you just pay for what you use, and you have like a licensing model. If you go with the licensing model, you basically get everything that's included in Anthos. It's yours, do whatever you want with it. You get GKE everywhere, so GKE on AWS, GKE on Azure, GKE on-prem. You get Anthos Service Mesh, you get something called Anthos Configuration Manager, and then you get a bunch of other stuff. So you can play with Anthos, or you can play with Istio just using the open source tool. Just go to istio.io, download the binaries. There is the Getting Started, which is basically guide you through deploying the Istio Service Mesh on a cluster, make sure it works, and then it has a bunch of what they call tasks. It's in the website. You can just go and like do things. You deploy a sample application, and you can do traffic splitting and all these kind of things. Or you just, when you are ready and you are grown up enough, you can just use Anthos Service Mesh to go to production. Yeah.
What the buzz about serverless Kubernetes?
That has nothing to do with this, but that's GKE Autopilot. Yeah. It's technically not serverless, but yeah, GKE Autopilot is our offering where GKE, we run the control plane, you have the worker nodes in your environment. GKE Autopilot is the next version where we run everything. And you only pay for the pods, you don't even pay for the nodes. Yes?
Yeah, I'm just going to make your life difficult again and say
you
could run serverless in there, because most of this, what serverless is effectively a runtime in a container.
Yeah.
So you could do it, but why would you?
Yeah, sure. And the last thing is my beautiful article why you shouldn't use the service mesh. This is the link. You can check it out. It's on purpose titled why you shouldn't use a service mesh. It's a provocative title. It actually goes through the consideration of the things you have to keep in mind before you architect around the service mesh. And that's it. Thank you.